Have you ever looked at a solid object, a rock, a table, or even your own hand, and felt absolutely certain that it was just a solid chunk of matter? Well, prepare to have your intuition completely shattered. Welcome to this explainer on matter waves and quantum reality. Let's unpack the bizarre, counterintuitive reality of quantum physics and take a journey into how a single, almost absurdly bold idea fundamentally changed our understanding of the entire universe. Because as it turns out, reality is a whole lot more fluid than it looks.
Okay, let's dive into this. Here is our roadmap. First, a bold scientific idea. Second, the de Broglie equation. Third, proving matter is a wave. Fourth, real-world quantum technology. And finally, we'll wrap up with the atom microscope challenge.
Section 1. A bold scientific idea. To really appreciate how revolutionary this stuff was, we kind of have to travel back a bit to set the historical stage. We need to understand the rigid scientific worldview that everyone just accepted as absolute truth, right before the quantum revolution turned everything upside down.
So until the early 1920s, scientists firmly believed the universe was neatly divided into two totally distinct categories. On one side you had light. Light was a wave. It rippled, it bent, it had frequencies. Then, on the other side, you had matter, like an electron. Electrons were particles. They were tiny, solid billiard balls of stuff. And there was absolutely no crossover. Waves were waves, particles were particles. It was a very tidy, comfortable way to view the universe, right?
But here is where things get wild. Now, what's really interesting about this slide is how a young French physicist named Louis de Broglie completely disrupted that status quo. He noticed that nature really loves symmetry. Einstein had actually just shown that light, a wave, could sometimes act like a particle, which we call a photon. So de Broglie proposed a revolutionary symmetry. He basically said if light can be both a wave and a particle, then matter must be both a particle and a wave. He suggested that all physical stuff literally has a wave associated with it.
You really have to understand how unbelievable this hypothesis was to the scientific establishment at the time. I mean, proposing that a solid piece of matter was undulating through space as a wave, that was practically scientific heresy. People thought he was completely crazy, like revoke his degree levels of crazy. But as this quote perfectly captures, it truly was one of the boldest ideas in the history of science. Section 2. The de Broglie equation. Now, de Broglie wasn't just throwing out wild philosophical ideas for fun. He actually backed it up mathematically. Let's look at how he framed this bold idea. And hey, don't worry, we're just going to look at the relationships here, not any scary, complicated math.
So, the crucial point is this remarkably simple equation right here, the de Broglie equation. Wavelength, which is represented by that Greek letter lambda, equals Planck's constant divided by the product of mass and velocity. Now, Planck's constant is just a fixed, tiny number. The real magic happens in the bottom half of that fraction. It tells us that the wavelength of any piece of matter is inversely proportional to its mass and its velocity. Basically, the bigger or faster a particle is, the smaller its wave becomes.
To give you a visual anchor for this deeply abstract concept, this is conceptually what it looks like when a physical particle travels through space. It's not just a solitary dot moving in a straight line. There is an associated wave function, a matter wave, oscillating and propagating right along with it. Literally every moving object has this wave guiding its probability. Even you and me. But because our mass is so incredibly huge compared to an electron, our wavelength is way too microscopic to ever actually notice.
Let's break down exactly how these variables interact in real time. You can think about it in 3 simple steps. Step 1, a particle's velocity increases. Step 2, because it's moving faster, its overall momentum increases. And step 3, because momentum is in the denominator of de Broglie's equation, as it goes up, the resulting wavelength gets shorter.
Let's move 2 and see how this builds into the physical shape of the wave. Over on the left side, we have a relatively slow electron, and it has a certain, fairly stretched out wavelength. But as we apply force and its velocity becomes greater, its momentum shoots up, and notice what happens to the wave on the right. The math strictly dictates that the waves become tightly packed together. The de Broglie wavelength drops significantly. The faster you push a particle, the shorter and tighter its matter wave becomes.
Section 3. Proving matter is a wave. Now, math and theory are wonderful, but physics demands hard evidence. And this brings us to the climax of our scientific breakthrough arc, the exact moment where theoretical math forcefully collided with physical reality.
As I mentioned earlier, a lot of established scientists highly doubted de Broglie's crazy wave-particle idea. It remained this sort of controversial hypothesis for a few years.
That is, until 1927, when two experimenters, Clinton Davison and Lester Germer, set out to put this crazy theory to the ultimate definitive test. They were going to settle it once and for all.
Here is the fundamental setup of their famous experiment. They took an electron gun and fired a beam of electrons, which, remember, everyone agreed were solid particles, straight at a thin sheet of nickel crystal. Now, if electrons were purely solid particles, they should bounce off the crystal atoms randomly, sort of like tennis balls hitting a really rocky wall, just scattering in all directions.
But that's not what happened at all, and the scientific world was absolutely stunned. And this brilliantly illustrates what they saw. When the electron beam hit the highly organized nickel crystal lattice, it didn't just randomly scatter. Instead, notice the detector arc on the right. The electrons formed concentric diffraction rings. They created distinct peaks and valleys of intensity, an interference pattern.
You really have to let this sink in for a moment. Diffraction and interference patterns are purely wave phenomena. Two solid objects cannot pass through the same space and cancel each other out, right? But the peaks and troughs of two waves absolutely can. By producing diffraction rings, these solid electrons proved they were behaving exactly as de Broglie predicted. Matter truly is a wave. The old, tidy boxes of science were officially destroyed forever.
Section 4. Real-world quantum technology. Now, you might be wondering, okay, that's incredibly weird, but it's just abstract historical physics, right? Not at all. Let's explicitly connect this strange, counterintuitive reality to the everyday life you are living right now.
The discovery of matter waves wasn't just some fun trivia fact for textbooks. It is literally the foundational bedrock of our modern world. Just look at this staggering list of innovations derived from this one idea. We use electron diffraction to analyze crystal structures. The entire field of quantum mechanics, semiconductor physics, nanotechnology, and the cutting-edge frontier of quantum computing. None of this would exist if matter didn't behave like a wave. Honestly, without de Broglie's hypothesis, the computer or phone you are using to watch this explainer right now simply wouldn't work.
To highlight a perfect, super practical application of the wavelength shrinking math we learned earlier, think about the electron microscope. Optical microscopes are permanently limited by the wavelength of visible light. They just can't see anything smaller than that physical wave. But because we know we can accelerate electrons to incredible speeds to make their matter waves incredibly short, we can use electron beams to literally see things thousands of times smaller than light ever could. It is the literal, real-world harnessing of de Broglie's equation to peer into the stunning atomic world. Section 5. The Atom Microscope Challenge. As we get ready to wrap up this explainer, I want to turn the tables for a second and challenge you. Let's apply what you've just learned to a hypothetical future scenario.
So here is a provocative thought experiment. Imagine a future technology where we could safely accelerate whole individual atoms, which are obviously much larger than electrons, and precisely control their matter waves. If we could somehow do that, could we build an atom microscope that possesses an even higher resolution than our current electron microscopes? I'll leave you with this final clue to ponder. Remember our rule? Resolution depends on wavelength. The smaller the wave, the higher the resolution. Now compare the mass of a large atom to the incredibly tiny mass of an electron, and imagine putting that much bigger number into the bottom fraction of the de Broglie equation we explored today. What do you think happens to the wave? I highly encourage you to think through the math on that one. Thanks for joining me on this deep dive, and I'll see you in the next explainer.